welcome. My name is Randy Ellis. In this session, we'll recall material for functions and specifically for linear maps. The main concepts for this session are a function is a map from a set to a set. Basically, this is from real numbers to real numbers, and vectorially, this goes from vectors to vectors. A linear map satisfies two criteria that we'll recall. A matrix is a representation of a linear form or linear map. A block partition is a particular way of finding subsets of a matrix, and the null space is a vector space that's associated with a matrix. Let's recall a scalar function. So for us, this is a map to a real number. So the codomain of a function is a set of real numbers. And here we have some set that is in the domain, and then this is the real number line, and we map from that domain to this codomain. So here both of our, for a scalar function, both the domain and the codomain are real numbers. We would write this as f is a map from real numbers to real numbers. Another way to say this is that the argument of it is some w, which is a real number, and this goes into the range of the function. And this would be a real number is the domain, a real number is the codomain, and a function is a map between them. It can also be written as saying a particular w maps to a particular element in the codomain of the function. Now, what happens if we have a vector? Well, historically, this was considered a multivariate function, but in modern terminology, what we do is we gather all of these entries into a vector. So here there are n of them, so there are n real numbers, and we write this as a function of a vector argument. And written in map form, f is a map from a vector space of size n to a real number. And pictorially, we can imagine that we have a vector space, so there are n, these are size n vectors, and then we have the codomain is real numbers, and what we're doing is we're mapping from that vector space to the real number line. We can say that one particular vector is mapped to a particular real number. Now, a vectorial map is a further elaboration of these concepts. Here what we do is we want to map a vector w that has n entries to a vector c that has m entries. So n and c can possibly be different. We write this as f is a map from the coordinate space of size n to the coordinate space of size m. And this can be written as a particular w is mapped to a particular vectorial result, and we can represent this graphically as we have two vector spaces, and what we're doing is we're selecting a vector w from the domain space, and then that is mapped to a vector c that is in the codomain. A linear function is a particular kind of function. It has to satisfy a couple of properties. So let's work first with a scalar function. So that's mapping a real number to a real number. Suppose u and v are any real numbers. The first property of a linear function is that if we map the sum of u and v, that equals the result of mapping u and mapping v. And if we have any real number and we scale u by that real number, that has to be the result of mapping u and multiplying by beta. So that's what it means to be linear. We can show that this is the same as if we take any w that's a real number and we map it. What we're doing is we're multiplying it by some real number a. In our usage, something that is not linear is this. This is sometimes called a line, but we'll call it an affine function when we need to. Now, a linear function can also have a vector argument. So here what we'll do is we'll imagine that we have a vector u that has n entries, a vector v that has n entries, and we're going to parallel what we did with a scalar function. That is, if we map the sum of the vectors, that has to equal the sum of the maps of the vectors. And if we scale the vector, that has to be the same as scaling the result of the map. And what we can do is we can show this is the same as a linear combination of the entries of the argument W. So we could write it as a sum, or we could write this vectorially as A transpose times W. A linear map, also called a linear form, is a further elaboration of these concepts. Suppose that we have vectors of size n, so they're in the coordinate space of size n, and we have vectors of size m. Suppose that W is a vector size n, and it's mapped to a vector c that's size m. We would write this as a vector function, note the little arrow over it, a vector function of a vector argument has a vector result. Now, each element of C is possibly independent, and that means that we could think of this as composed of m functions. So the first entry of C is function 1 of W, the second entry of C is function 2 of W, and so on until the mth entry of vector C is f sub m of W. And each one of these must be linear, and we would say that this function is a linear map. So what's an example of a linear map? Well, a simple example is we're going from the plane to a plane. So suppose that we have a vector W that's in the plane, a vector C that's in the plane. We can represent W using 2 entries. We can represent C using 2 entries. As usual, for us, these are columns. And each one of these functions must be linear. So that means we could represent this as function 1 is some coefficient A11 times the first entry of W plus some other coefficient times the second entry of W, and that gives us the first entry of C. Likewise, the second function gives us a second linear function of C. What we then would say is that the result C is the result of taking a matrix A times the vector argument W, and now A, we say, has 2 rows and 2 columns, or it's a 2 by 2 matrix. Now, what happens when we have larger spaces? Well, the same situation obtains, is that now we have, if C has m entries, then we have m of these functions. Each one of these functions has to be linear, and the result is that this result C is a product of a matrix A and the vector argument W. So this is what it means. A linear map or linear form can be represented by a matrix. A matrix partition is a way of breaking a matrix into smaller pieces. Let's recall what a partition is for mathematics. If we have a set S, a partition is a set of subsets. Each one will denote as P sub I, and each one of these pieces has to be non-empty. And when we take the union of all of them, we get our original set. And then there's a further requirement that the intersection of any of these two partitions has to be the null set. So it has to be completely empty. That is, so what that means is every member of the set S is in exactly one partition. So we can take a matrix, we can consider it as a set, and we can partition it into blocks. So suppose, for example, we have a 4 by 4 matrix. We can break this into blocks, B, C, D, and E. And here, although you might naturally think, well, B is 2 by 2, C is 2 by 2, actually there are quite a few ways that we can do it. B, for example, could have 1 row and 3 columns, and C could be 1 by 1, etc. So the way that we like to partition matrices here is we'll usually decompose this into columns, and each column will be a vector. So this is a block partition, and for example, if we have a matrix with m rows and n columns, we'll break this into n parts, and each part is of size m. So we can think of the matrix A as being n vectors, and we'll denote these with subscripts. It's also possible to partition them into rows, but we won't do that very often. So when we do this, we can now think of matrix block as a non-empty rectangular section. So when we say a matrix block, that means we're partitioning the matrix, and we're partitioning it into rectangles. So we can partition it, for example, by its columns, which is what we'll, it's almost the only way that we'll do it. And so we take this possibly very large matrix and we represent it more compactly or more concisely using vectorial notation. Now, let's try writing a simple map using a matrix and a vector. So the simplest map that's sort of interesting is a map from size 2 vectors to size 2 vectors, and we already understand from linear algebra that this is also a matrix vector multiplication. Well, let's work out that matrix vector multiplication, and you can use your favorite method. One method is to take this row times this, and then this row times that. If we did it that way, what we would write this vector C as is it would have two entries. This is the first entry, that's the second entry. Well, another way that we can write this is we can see, oh, W1 is appearing twice, and we could gather these entries into a vector. W2 is appearing twice. We could gather these entries into a vector. And what that would give us is that the vector C is a linear combination of the columns of the matrix A. We can also think of these this W argument as providing the weights in this linear combination. Now, how would this work visually? Well, we have our result C, and this is the product, the matrix product of a matrix A and a vector W. Well, what we can do is we can think of W1 is weighting the first column, W2 is weighting the second column, and so on until Wn is weighting the final column. So this starts to bring in the first of the major vector spaces that we'll associate with a matrix. So suppose we have a matrix, m rows and n columns, and we have some W vector that's in the domain. We can consider A to be a linear map, and we can write it in various ways, as we've just recalled. So the matrix vector product is a linear combination. What that means is that this result C here has to be a weighted sum, a linear combination of the columns of the matrix A. And that means that the vector C has to be in the same vector space as the columns of the matrix. The column space of A we can interpret as the vectors that are all possible linear combinations of the columns of the matrix. The null space, also called the kernel of a map, is also, in our case, a vector space. So now let's consider that same general situation where A is a linear map from size n vectors to size m vectors, and this has a second important vector space. So a null vector we can define, we'll use the symbol z here. So this is a size n vector, and it maps to 0. And what that means is that if we use this vector z, if we use its entries as weights for the columns of A, what we get is the 0 vector. We often will write this null space using the script n. And trivially, the vector 0 is in this space, and that's because if we take the 0 vector and use its entries as weights in a linear combination, we always end up with a 0 vector. So what are some examples of this? Well, let's consider a first matrix, and this is a 2 by 2 matrix. The first column is 1, 0, the second column is 2, 0. The null space of this is any vector z1 where it has 2 times some real number and then the same real number negated as its second entry. You can check that if we use the entries of this vector z as weights in a linear combination of the columns of A1, what we always get is the 0 vector. A slightly more complicated example is a matrix that has 2 rows and 3 columns. So consider A2 where the first column is 1, 1, the second column is 0, 0, the third column is 1, minus 1. You can verify that the null space of this second matrix is any vector that has 0 in its first entry, 0 in its third entry, and any real number in its second entry. How can we summarize this session? Well, what we've learned is that if we have a linear map A that maps an argument W to a result C, each row of the matrix is a linear function, so it satisfies those 2 properties of linearity. Each column of the matrix A can be considered to be a vector because we can partition the matrix. Each entry of the argument we can consider to be a weight in a linear combination of the columns of the matrix. Thinking of A as a linear map, it has a null space, although it may only be 0, and the columns of A live in a vector space.